Okay, this is the optimal case. Now compute the force which is exerted to the cup or to the cups in this case. Again, as a fixed observer, I'm looking at this case. I see that there is an incoming jet with the velocity of v sub j, and there is no outlet velocity, or there isn't any outlet stream of water, because I'm speaking about the optimal case, and the velocity of the outlet velocity, absolute outlet velocity, is 0. So then I'm a fixed observer, and I'm just looking at this system. From my viewpoint, the exit velocity is 0 in the optimal case, or the optimum case. Okay, so here here F is equal to the product of, this is the mass flow rate again. So Q is the volumetric flow rate with respect to the fixed observer, and this is the exchange of velocity. This is the incoming absolute velocity. This is the incoming absolute velocity, and this term is the absolute outlet velocity, or the residual velocity. As I mentioned, in this case, I'm solving the problem from the viewpoint of a fixed observer. So these are absolute velocities, and this is the absolute incoming flow rates. This is again straightforward, and the power is equal to the product of, again, velocity and the force, which is computed in the previous relation. Again, replace this expression in the expression for P, and now replace the optimum value for the circumferential velocity in this relation. So U here is equal to the half of the jet velocity, and again this one is equal to the half of the jet velocity, and Q, or the flow rate, is equal to the product of the jet area and again the jet velocity, and the result is P, optimum power, which is half of the product of the density and the jet area and the jet velocity to the power of 3. Compare the results. You see they are different because the initial case is the initial cases are different. So the real optimum or maximum power for a real Pelton turbine should be computed from this relation. This is a fake result. I've written this case in order to, for the sake of comparison of these two cases. Okay, there is another alternative solution for the second case. You can compute the second maximum power, which is for the real Pelton turbine, using the solution procedure of the case 1. So here we have the F is twice, again I've written F equals twice. Here is the mass flow rate, the relative mass flow rate. This is an absolute mass flow rate. The only difference between these two cases is the absolute. Here, this is the relative mass flow rate. This one is the absolute mass flow rate, or the full mass flow rate. The other name is the full mass flow rate. Again, times V relative, again V relative. So copy and paste this expression here. I'm going to compute the result of for the real turbine, Pelton turbine, using this relation. So copy and paste this expression here. Just change the subscript of the flow rate from the relative flow rate to the absolute flow rate, which is called the full mass flow rate. So the relative velocity is Vj minus r omega, r times omega. Then the power is the product of this computed force and again r omega, or u. Now take the derivative of, similar to the here, take the derivative of p with respect to omega, or with respect to r omega, which is u. Assume that the radius of the wheel is a constant parameter. So the derivative of the power with respect to the circumferential velocity equals 0. This is the optimum case, or the optimal case. This results in the this expression, which says that the circumferential velocity is the half of the jet's velocity, which is exactly similar to the result obtained using the first procedure, solution procedure. So the results are the same. In the previous section, I computed the maximum power which can be extracted from an incoming jet using a Pelton turbine. In this case, when you have the maximum power, you can easily compute the efficiency, because we have a real power and a maximum power. This is a real quantity, and this one is the optimum case. So the ratio of these two quantities is called the kind of efficiency of the Pelton turbine. So based on the previous section, the power is the product equals the product of the force and the circumferential velocity, and F equals the twice the product of the density, the volume flow rate, or the full mass flow rate, and the velocity with the jet velocity with respect to the rotating frame. This one again is computed in the previous section, which is the maximum power, which can be obtained by taking the derivative of this expression, or by another alternative solution, which I've explained both of solution procedures in the previous section. So this is the maximum power. The numerator of this relation is the power, and the denominator is the maximum power. Simplify different terms in this fraction, and this expression is the final form of the efficiency of Pelton turbine. Pay attention to the limiting cases. When the efficiency is 0, we have two cases here, which results in a zero efficiency. The first one is the circumferential velocity equals 0. This means that the turbine does not rotate, or it's stationary, which is meaningless because turbo machinery are rotating machines. So this is not important. And the second case is when the jet velocity equals the circumferential velocity. This means that both velocities are equal, so the relative velocity of the incoming jet with respect to the rotating frame is 0, because both velocities are moving along each other, so they cannot exchange momentum, so the efficiency is 0. The other case is when the jet velocity goes to infinity, which is again is not a physical case, so I've ignored this case. And the next one is when the efficiency is maximum or equals 1. So easily equal this relation to 1, and you can compute that the circumferential velocity equals half of the jet velocity. This is exactly the result I obtained in the previous section with two strategies. And the first one by taking the derivative of this expression, and the other one by a somehow more physical procedure. This is the optimal case as expected.